Hello, wonderful people. Welcome to the next talk in this series of talks on the awesome science that the dark energy supernova team have done with their wonderful catalogue. This is a really cool talk. I think after recording and editing, this might even be my favorite from this series. In it, we learn about how the team, led by Paul Shah, who is a postdoc at UCL, have detected a weak lensing signal from this amazing supernova catalogue. This specific signal being a magnification and de-magnification of the supernova light curve, but stick around and watch the talk for the details. This is the first time that this signal has been measured with any meaningful statistical significance. So the reason I especially like this talk is it's essentially telling us about the birth of a new cosmological observable. Cosmology talks wasn't around the first time the baryon acoustic oscillations were seen, or even when cosmic shear was first found. And it certainly wasn't around when the CMB anisotropies or polarization were first being detected. But today we can watch a talk about the first detection of the lensing magnification of supernovae. And then 10 years or so from now, when the LSST people or whatever comes next after that are giving talks about the precise cosmological constraints they're getting from this probe, we can all look back on this talk and remember we were there at its birth today. That's really cool. Paul is joined in this talk by Tamara Davis. So welcome, Paul and Tamara. Do you want to start by telling us briefly about the paper?
Thank you. So we're going to tell you today about what type 1a supernova could tell us about inhomogeneity in the universe. And to do that, we're going to think about how they get magnified by gravitational lensing. So let's think about what happens when light from a distant source travels to us through the universe. It meets matter along the way, and we know that matter bends light, and these sources can appear to us as either magnified or maybe demagnified, depending on whether they pass close to foreground matter or whether they pass through a void. Now, in our paper, we detect weak lensing effects in supernova magnifications at greater than 5 sigma for the first time in the literature. Furthermore, our data constrains the profiles of these dark matter halos and shows that they are consistent with N-body simulations. Now, we can do more than that. We can also, using a calibrated lensing estimator that we build, we can correct distances for weak lensing. So in a similar way that adaptive optics corrects photometry for atmospheric distortions, our lensing estimator will correct distances for distortions induced by weak lensing. Now, this is useful in two ways. It reduces observational scatter so we can get tighter constraints on cosmological parameters. And we could also check that if we correct these distances, we get similar cosmology to if we didn't correct them.
Yeah, so one question I'm curious about already, but maybe this might come up later on in your talk. So if it does, let me know. But how is the lensing you've detected now comparable to cosmic shear? Is it giving the same information or different information? Is it detected at the same significance? What is the kind of comparison there?
Well, we don't have as much significance as the weak lensing of galaxies because they just have so much more data. We're going to see that we have about 1,500 supernovae. So where we are with this at the moment is comparable to galaxy weak lensing around about 2005, where we have the first detection. But we're hoping that with future samples with lots more data, we can start to get competitive with weak lensing by galaxies.
Okay, I was thinking that even though they might have more data, you might have the advantage that we don't know the intrinsic shape of the galaxy that's been lensed, but perhaps we do know the intrinsic, I don't know, light curve of the supernova. I mean, we don't know it, but it's at least kind of more known.
For sure, the galaxy lensing guys have more noise in their data, but they also have a lot more data. We have a lot less data, less noise, it's true, but still our constraints are a little bit weaker. But the really interesting thing about supernovae, as we'll see in the talk, is that they pick out scales that the galaxy lensing guys can't pick out. Supernovae are essentially point sources at cosmological distances. So we are quite sensitive to small scales in our analysis. So we are looking at a slightly different playground, if you will, than the galaxy lensing people.
If people are thinking of this talk or your paper 6 months from now, and there are only two things they can remember, what would you want those two things to be?
This is the first time that we've been able to open the door to the study of weak lensing of supernova at cosmological distances. There's so much exciting cosmology that we can do with this. Secondly, is that we can correct distances for inhomogeneity in the universe, so we can check if our samples are biased or not.
Cool. And I guess, as you said earlier, the corrected and uncorrected ones give similar cosmology. Is that just because other uncertainty is larger at this point of time?
Yeah, for this size of data set, Other uncertainties larger. But again, as we look into the future with bigger surveys, we would expect those constraints on cosmology to narrow compared to our lensing correction. So although it's maybe not so significant today, in future, I think this will be quite an important part of cosmology.
Okay, so this isn't the source of the Hubble tension or the evidence for perhaps evolving dark energy.
No, no. Although as we shall see, it does weaken a little bit the evidence for evolving dark energy, but not by much.
Why have you done this? What questions are unsolved that you wanted or needed to solve? Why were they unsolved at this point? And why is this happening in 2024 and not, say, 2 years ago or 2 years into the future?
Well, it all kind of started with just thinking about supernovae as point sources. You know, when you look at lensing of galaxies by other galaxies, you're limited by the size of your source. With supernovas being so small, we can start to delve into some of those really tricky questions that have been bothering us in cosmology. You know, we can start to investigate potentially substructure in dark matter halos. You know, we can consider whether a portion of dark matter is made out of black holes. You know, whether the power spectrum maybe is affected by baryonic suppression more than we expect. These are all questions that have been bothering cosmologists now for a little bit of time, and supernovae open the window to start testing some of that hypotheses.
This may be another thing you're going to go into in more detail, but already, even in cosmic shear, you're saying that you're sensitive to even smaller scales. Already, they kind of have to do cutoffs, that they've got the data at smaller scales, but they just can't model at smaller scales. So I imagine that you've got an even bigger problem than if your data is sensitive to even smaller scales. But perhaps, yeah, you can turn it on its head and say, actually, we can kind of measure how much the baryons are influencing things and stuff like that, instead of treating it as a nuisance.
Yeah, yeah. The theory modeling of a power spectrum on small scales is a problem. So, you know, we're hoping that our data can shine a window to inform how we solve that problem.
This kind of new analysis has been made possible by the enormous number of supernovae that we have from the Dark Energy Survey, and particularly how many supernovae we now have at high redshift, because the lensing signal is stronger at high redshift, and previously there just wasn't enough high redshift supernovae really to make the measurement.
Okay, is the lensing signal higher redshift just because the ray travels further, so it's got more time to get lensed, or
Yeah, since the light travels through more inhomogeneous universe, just the longer it travels, you expect a bigger signal from things that have had to travel further.
okay? And what is it that's unique about the dark energy survey that you've got all of the large redshift supernova? Because I mean, normally when one hears dark energy survey, one's thinking cosmic shear, and there's lots of competitive cosmic shear surveys like KIDS and HSC. Do they have their own supernova catalogues, or is there something unique about the dark energy survey?
Yeah, so to get supernovae, you have to measure the same patch of sky night after night and look for things that change. So, as part of the Dark Energy Survey, one of the core components that we did from the beginning was a special time lapse survey of few patches of the sky in which we could find supernovae. And we were looking deeper than has ever been done before with a supernova survey of this sort. And so we managed to get what's now more than 80% of the known supernovae that we can use for cosmology above redshift zero point 0.5. So it is a huge addition. We have over 1,500 supernovae in our sample. So that's a huge addition of high redshift supernovae, which makes this kind of measurement possible at a high significance for a first time.
Yeah, I should also say that DES is a survey that's done on one telescope platform. Many of the other supernova sets that are out there on the market are combinations of surveys done on different platforms. And it's kind of hard sometimes to cross-calibrate this because DES is so uniformly calibrated. And as we shall see, the effect of weak lensing is pretty small. It really helps to have all of this in a homogeneous, uniform calibration.
Okay, yeah, I feel like I now have a kind of dumb, naive question, but so the supernova that you've detected are supernovae that, what am I trying to ask? The length of time that it's supernovaing for is short, or is it something that, like, for the whole length of the dark energy survey they were going off and you just had to look at that area of sky, or did you have to actually see it at the right time as well because it was transient, sufficiently transient?
Yeah, you have to catch them at the right time. They're bright for about a month, They have longer, they fade for much longer than that, but the really bright time is, a month or two. And the so you every time you're looking, you're seeing some supernovae that are on the way up, some supernovae that are on the way down, and some galaxies where the supernova hasn't gone off yet or will go off in the future.
Yeah, let's get into the details then of how does the weak lensing actually get measured, and what have we learned about it?
Okay, so as supernovae, what we do to constrain cosmology is we build a Hubble diagram, and this looks at the brightnesses of a supernovae as compared to their redshifts. Now, we're all, I guess, familiar with the usual formula that we can write down for luminosity distance in a homogeneous universe, right? Whatever the background cosmology is, we can write down a distance for that. I guess the question is do we have a fair sample of a homogeneous universe when we're looking at a collection of distant supernovae? Maybe they're seen on overdense lines of sight, perhaps because those supernovae are more likely to be magnified and therefore more likely to make it into the sample. Or on the other hand, maybe if they're spectroscopically confirmed, they might be on more underdense lines of sight because a crowded foreground might be more difficult to confirm the spectroscopic redshift. So homogeneous universe is a good place to start for an assumption, but what does a clumpy universe do to supernovae? Well, as we've seen in the animation, if a background supernovae, if the light of that passes close to a foreground clump of matter, we can expect that supernovae to be magnified slightly. Now, type 1a supernovae are standard candles, as we know, so we've got a pretty good idea what their intrinsic brightness is. So we might stand a chance of detecting this. Now, conversely, if a supernova has gone through some voids on its way to us, i.e. less galaxies than average, we might expect that supernova could be a little bit dimmer. And there's another thing that's going on as well. If matter is more clumped up in the universe, it stands more chance of intersecting with one of these matter clumps on its way to us. Therefore, more clumpiness in the universe means more scatter in the Hubble diagram. So we might hope to measure that too. So let's have a think about what kind of size of effect that we're looking for. Here's a little graph of just the probability of magnification in terms of mags. And this is going to be for about a redshift of 0.6. It's typical redshift of our supernova sample and typical values of cosmological parameters. So as we can see, the effect is pretty small. This PDF has a distribution width of only about 0.03, about 3% in brightness. So it's pretty small compared to the intrinsic scatter of supernova. Now, another thing that we notice is that the distribution peaks above the mean of the distribution, which means that most supernovae are seen through voids and are therefore dimmer than they would be in a homogeneous universe. On the other hand, some supernovae cannot be lucky enough to pass close to foreground clumps of matter and they'd be brighter. So we have a skewed distribution.
And I guess the reason why most of them pass through voids, maybe this is obvious to the viewer, but maybe it's not, is just that a collapsed object is smaller than a void, which is the kind of expanded object. So most of the volume of the universe is empty, even though most of the matter in the universe is in clumps.
Yeah, that's exactly right. The clumps are smaller, and we need the light ray passing fairly close to that foreground clump for it to have an effect on the magnification. The voids are bigger, and so there's just more chance that the light ray is going to go through a void than it is going to pass close to a clump. Okay, so as we said, we can't really point at an individual supernova and say, well, that one's magnified, that one's de-magnified, because the intrinsic variation in the luminosities, well, that could be caused by some differences in the explosion or maybe just even observational scatter. That's going to be around 15% for an individual supernova, and we just said that the magnification is typically an effect of just 3%. So how are we going to detect this? Well, we're going to need a decent sized sample and we're going to do some statistics. So what we do for data is for a given supernova, we look at all the galaxies that are in our catalogue in the foreground of that supernovae. And we assume that those galaxies are going to be embedded in dark matter halos. Now, we're going to perform a calculation and try and estimate the lensing that we would expect given the number of galaxies and whether they are big galaxies or small galaxies, depending on their photometry, whether they're close to us or far away or somewhere in between, again, depending on their photoses. And we're going to try and estimate what the magnification might be for that individual supernova. So here's a brief look at our data. So on the bottom panel, we have a supernova data sample, Now, for the DES 5-year sample, this is around 1,800 supernovae, but we're not going to consider the lower Z part of that because we don't really expect those supernovae to be affected by lensing. So we're just going to look at supernova bigger than zero point 0.2 in redshift. Now, that's about 1,500 supernovae. So if we look at the number of galaxies that are close to those supernovae in our foregrounds, we get about 800,000 galaxies. And that's shown in the upper panel there, where we just plotted the absolute magnitude of those galaxies as inferred from their photo Z compared to where the magnitude cutoff is for the depth of the DES survey.
I think you never said this, but I think it's literally written on your slide right now. So all of the galaxies that you're using were all detected with the one telescope as well, the DES Year 3 Gold. So it's not like you've cobbled together a bunch of different galaxy surveys to say how many galaxies. It's all from the one survey. Is that right?
Yeah, and this is the beauty of DES. Again, when we look at other supernova data sets that have been made from different surveys, some of those surveys may come with published galaxy catalogues, some may not. So with DES, it's just fantastic. We have this galaxy catalogue already there, made for us to sit alongside our supernova sample.
Is there a reason why it's helpful that it's the same telescope for the supernovae and the galaxies, or is it just useful that it's one telescope for each, or is there some reason why it's quite nice that it's the same for both?
It's a kind of coverage thing, so it didn't have to be, I think, the same telescope, but it is convenient that the galaxy survey comes together with the supernova survey and covers the supernova fields in full. Okay, so moving on, and here's just a little bit of maths. We need a model for the matter density, so we're going to assume that the matter density is a combination of a linear power spectrum matter density plus a collection of collapsed and virialized halos. Now, for those dark matter halos, we're going to assume a certain radial profile for those halos. Now, that halo profile is going to have a little bit of freedom. So we're going to use a shape parameter beta, and that just sets how quickly the dark matter profile decays as you move away from the center of the galaxy. A higher beta means it decays more quickly, and a smaller beta means it decays less quickly. Now, the standard NFW profile, which a lot of simulations predict is what dark matter halos should look like, is beta equals to 2 in our model. But we're going to let the data decide, right, rather than simulations. Another parameter that we're going to need is we need some way to weigh the halos that are in front of us. Now, we just have the photometry of those foreground galaxies. So we just use a mass to light ratio to convert the photometry of those galaxies as measured by their R band magnitude into solar masses using our mass to light ratio. And that in turn determines the size of the halo given the virial mass, M200, and hence determines in full the halo profile given those two parameters. We can therefore write down an estimator for the lensing along a given line of sight just by integrating this matter density from us, the observer, at distance 0 all the way to the source, multiplied by a lensing efficiency function, that's the fraction you see under the integral, and of course the matter density itself. So in summary, the inputs to our lensing estimate are the foreground galaxies, their positions, their photo Z, their brightnesses, and our two free model parameters, the mass to light ratio and whether the halo profiles are shallow or steep.
So I wanted to ask you about the lensing efficiency. How do you know what value to give it, or is it, and how free is it? Because if it's completely free over all redshift, it feels like it destroys any chance of any constraining power. Is it something that we can kind of know from first principles in some way?
Yeah, so this lensing efficiency function that we see just after the d-chi in the integral, that's what theory gives us. So theory tells us that if we've got a lens that's roughly kind of about halfway in between us and the source, that's going to have the most effect on lensing. So it's a little bit like weighting. So lenses that are very close to the sources, well, they don't have much opportunity to deflect the light so much. Similarly, lenses that are close to us as an observer, the light has already traveled and it doesn't have further to travel in order for the light to be deflected significantly. So it's really a weighting function, and it kind of says that the matter that's more or less halfway in between us and the source is the stuff that has the most effect on the magnification.
Okay, can I now ask a really naive question? Chi here is then kind of either directly the redshift or some rescaling of the redshift. Is that right?
This is the co-moving distance.
The co-moving distance, great. So then the lensing efficiency function doesn't have any free parameters. It's just this chi times chi s minus chi divided by chi s. That's it. Is that correct?
Correct. Chi s is the distance to the source, and chi is where the matter sits.
It's 100% fixed. It's not a free function whatsoever. I see.
It is fixed by general relativity and the expansion of the universe.
It's actually literally like having a lens, a glass lens with a light source behind it. And as you move back and forth, there's sort of a sweet spot where it focuses the light perfectly into a dot, right where the observer is. So that's why you have that lens. One of the reasons you have that lensing efficiency kernel.
Okay, so all of that put together, the integral over the line of sight of the matter density allows us to calculate a prediction for what the lensing is going to be given our assumed halo model. So what do we see? So this graph on the x-axis, that's our lensing prediction, our lensing estimator. And we just put in some typical values that we might expect for our free parameters. And we've just normalized the axes a little bit. The scales don't matter too much, but we've just done it in terms of the expected variation. On the y-axis, we have the Hubble diagram residual, again normalized to expected deviation. Now, the supernovae that are dimmer are going to have values of a y-coordinate that are bigger than 0, because those are the ones that are lying above the Hubble diagram. And each supernovae, here we've just picked out the ones in a particular redshift bin from 0.6 to 0.7. Each dot is an individual supernovae. So as you can see, we've got some points that lie above the Hubble diagram, some points that lie below the Hubble diagram with a y-coordinate less than 0. Those are the brighter ones.
And is this a residual after fitting like lambda CDM model to the data or something, or?
Exactly so, yeah. We fit a lambda CDM model to work out what the residual is. Okay, so conversely, on the x-axis, the ones that have negative values of the x's, these are the ones that are brightened. So when we have more foreground, i.e. more matter density, our lensing estimator is going to predict that these supernovae are magnified. On the other hand, where we have less density than average, and remember here we're just subtracting off the average because the average is exactly what the Hubble diagram gives us. These supernovae, we expect that they're going to be dimmer. So in other words, were we to see a connection between our lensing estimate and the Hubble diagram residual, what we would expect to see is a clustering of points up in the top right-hand quadrant. In other words, they have less foregrounds and they are dimmer. And also in the bottom left quadrant, they have more foreground galaxies and they are brighter. Now, honestly, if you just look at this particular redshift bin, I think it's pretty hard to pick out if that's indeed the case or not. So let's look at some other redshift bins. Here's a collection of redshift bins going all the way from 0.3 in redshift up to the furthest that we observe our supernova to 1.2 in redshift. Now, one of the things that our estimator predicts is that the deeper we go into our survey, the more lensing has an effect. Just as Tamara said earlier, right, the light rays have got further to travel to us through the universe. They've got more chance to bump into matter along the way. And so we expect the correlation between our estimator and the Hubble diagram residual to be strongest at the high redshift buckets. So if we look at the bottom right-hand panel in this collection of 6 panels, we do indeed see just by eye that there appears to be a grouping of dots towards the top right and the bottom left quadrant, just as we would expect.
And these are pretty scattered, but this is why it's taken decades to be able to detect this after we knew supernovae were standard candles, because the intrinsic diversity in the supernovae themselves are about 10 times bigger than the signal that we're trying to detect. So that's why it's such a subtle thing that's taken some great work by Paul to dig out of the data.
There's quite a sharp cutoff in the model delta M to the right of the plot. Is that why is that? My speculation would be that it's to do with like traveling through entirely empty universe, and you can't get more empty than a density contrast of -1 or 0 density. But is that it, or is there some other cause for that?
Yeah, that's absolutely right. Yeah, and particularly if you look at the top left-hand plot, you'll see that it cuts off very sharply. It's almost like a vertical line. There's a distance that's called the Dyer-Roeder distance, and this was worked out in the 1970s by Dyer and Roeder. And that's as if light had passed to us through a completely empty cylinder of matter. So nothing there. But the background expansion of a universe is still the same. So that's the most demagnified we can expect any source to be in our universe. It's literally traveled through us through an elongated void all the way from the source to us as an observer.
Yeah, and I guess the reason that's happening less often at higher redshifts is just that it's the kind of classic. You have to keep tossing the same heads every single time, and eventually you get rogue overdensities on the way. Having a completely empty cylinder is harder the longer the cylinder.
Oh yes, be very hard to travel to us all the way through void, all the way from redshift 1 to us as an observer. Okay, so when we put all this data into the standard correlation estimate, we detect the correlation is non-zero at a significance of 6 sigma. Now, as I mentioned in the previous literature, and as Tamara said, it's actually been very hard to detect this historically. There have been a number of papers, and they've generally got pretty low significance detections. So it's kind of reasonable to ask, why do we get such a big significance here? What have we done that's different to everybody else who's tried to find this and found it very difficult? We think we've got a better lensing estimator, so we pull more data into how we calculate lensing. And in particular, the sky positions are really important because we need a nice close encounter with a matter clump to produce a decent lensing effect. And as we mentioned, the DES survey being so homogeneously calibrated, it's a very, very clean survey to look for this. The scatter is reduced compared to some of the earlier surveys that we have. So the signal to noise is better with DES. Those two effects in combination explain the difference from the previous literature to where we are today. So we're passing the 5 sigma threshold for the first time here. Okay, so let's have a little look about what the data has to say about our model parameters. Now remember, beta was a shape parameter that determined how steeply the dark matter halos fall off with increasing radial distance from the center of the galaxy. What we find is that our data is consistent with the NFW profile where beta equals to 2. That's what we get from simulations. So that's nice to be able to confirm that it seems like our n-body simulations are predicting slopes of halos that agree with our data. We also get a constraint on the mass to light ratio. That also seems to be consistent with the literature, and I'll kind of come back to that a little bit later to say what we can learn from that. Now, as we claimed before, now that we've calibrated the lensing estimator based on our data, so our data being the 5-year DES supernova sample and the foreground galaxy catalogue called Year 3 Gold, we calibrate our estimator based on that. And now we can use that estimator for any line of sight within the DES Year 3 Gold footprint. And we can attempt to correct distances for this lensing estimate. What do we get if we try this for the WCDM cosmology? When we put our corrected distances into the cosmological solution, what we find is that the omega matter moves a little bit higher, and the equation of state for dark energy, the W parameter, moves a little bit lower. Now, in our original sample where the distances weren't corrected, these parameters were a little bit further away from lambda CDM. When we correct the distances for lensing, we move a little bit closer to lambda CDM. So I think this is kind of interesting in the context of the debate we're having recently, where the supernovae samples seem to be indicating an evolving dark energy component. Now, our change is not so significant in terms of the uncertainty of the parameters, but we are moving closer to lambda CDM, and therefore when we correct distances for lensing, we're seeing less evidence for evolving dark energy, albeit not at any great significance yet.
This detection of the mass to light ratio being the value expected, could one reframe that to say, in some sense, this is yet another detection of dark matter, in a sense, that you're detecting that there must be excess mass that isn't just the visible mass to be doing this amount of lensing? I mean, not that dark matter needs any more evidence, but is that kind of a...
Yeah, I guess we should say that the mass to light ratios are pretty variable. across the literature, because people have lots of different definitions for this. So this is not so straightforward to kind of compare with other results. People have different definitions of masses, different definitions of light, and so on. So the kind of significance of this constraint on the mass to light is, if you remember right back when we constructed the lensing estimator, we pulled out the nonlinear and the linear scales. So this is the mass to light ratio for the nonlinear scales. So what we can do is that we can say, okay, this provides us with a constraint on the amount of dark matter that's bound up in virial halos, and the amount that's kind of just floating free with some fluctuations, but is not part of those halos. And again, that's something that simulations predict, and we can check this using our data. Okay, so we find from this that about 40% of the matter in the universe is bound into virial halos, which is pretty much the same as what we get from simulations. So again, that's another nice confirmation that our n-body simulations seem to be on the right track and match the data that we're seeing. Okay, so what's next? Well, one of the things that we can do is that we can look at across our sample and we can see how variable our lensing estimator is. And this is what the y-axis is plotting. So when we look at that as a function of redshift in bins, we see that redshift 1, the scatter that we observe from lensing, is about 0.05, or in other words, 5% in brightness terms. Now, we have a theory prediction for what this scatter should be, and that's an integral over the matter power spectrum. So what we can do is that we can compare the luminosity distance scatter that we observe from our calibrated estimator in our data with the theory prediction. Now, this is pretty tricky because it involves small scales, but there are a few general things that we can say. Let's imagine that some portion of the dark matter is made out of black holes or other collapsed objects. They don't have to be primordial, but they could be. Now, if that were the case, what black holes do is that they really scatter light. So if we find that our observed scatter is greater than our prediction, that suggests something is causing that extra scatter, and what that something could be is primordial black holes. Okay, another thing that we can think about is the sigma rate tension. So just as a reminder, this is the fact that when we look at the inhomogeneity that's there imprinted on the cosmic microwave background, and we project how that grows under gravity through to our current universe, we find that the cosmic microwave background predicts that there's more clumpiness in today's universe than we see in galaxy surveys. Now, one of the ideas of how we kind of resolve that tension is that there might be extra power suppression on small scales compared to what our models predict. Now, if that were the case, because there is less clumpiness and more suppression of power on the scales of individual halos, we would expect less scatter than the integral over the power spectrum would predict. So in other words, we can take the scatter in our data and we can start to ask some questions, some really fundamental questions about primordial black holes and the sigma rate tension. And that's something that we're going to look at in future work.
Just a quick question about the black holes. I guess if the black holes were light enough in mass, then you wouldn't expect more scatter because the chances of getting close enough to the very small radius of high lensing would be unlikely. So you'd expect more scatter for sufficiently massive black holes, I guess. Do you know what sufficiently massive means? Like what value would you actually need in terms of like solar masses or something?
Yeah, this is something that we need to investigate, but we think roughly around 10 to the minus 2 solar masses. At that kind of mass, the Einstein radius, which is the kind of sphere of influence of lensing, gets smaller than the size of a supernova photosphere. Now, we did say that that was basically a point source at cosmological distance, but that's an approximation. It's not really true. The photosphere expands out to about 50 astronomical units. And when the black holes get super tiny, the influence of lensing is much smaller than the source. So yeah, at that stage, they start to behave just like homogeneous dark matter, smoothly distributed dark matter, at least as far as lensing is concerned.
Oh, 10 to minus 2 solar masses is still relatively small compared to a lot of primordial black hole candidates.
Okay, so just to summarize our key takeaways, we've detected the weak lensing magnification of supernovae for the first time at greater than 5 sigma. So this is passing the threshold for robust detection. And this is because we had a decent lensing estimator incorporating all of the available information. and also because of the size and depth of the DES 5-year sample. Now, our results are consistent with N-body simulations, and that is the amount and the shape of the dark matter halo profiles. We can go further and we can correct distances using our calibrated lensing estimator for weak gravitational lensing. When we do that, we find some small shifts in cosmological parameters, which means slightly less preference for evolving dark matter, but not really at any great significance. But we expect this to be a big effect in further samples where the statistical uncertainties narrow, the samples are deeper, so lensing matters more, and we are really able to determine these parameters to a great deal of accuracy. And furthermore, the study of the magnification of supernovae opens the window to lots of really interesting questions. Do black holes form any portion of the matter density of the universe? And is the power spectrum suppressed on small scales? By small scales, we might mean wave numbers greater than 1 in inverse megaparsecs. So we're really looking forward to taking this work. It opens the door. We want to carry it forwards and ask some really fundamental questions about the universe.
So on that last point, I guess the previous slide was the key kind of figure for that. Is it true to say that you can't really make any like speculation, because it looks like the blue line is neither above nor below the black and green lines? Like you're not seeing evidence of an S8 tension or primordial black hole dark matter, not because it's not there, just because the scatter in the scatter is just too big.
Yeah, at the moment, what we really need to do is look at the systematics. So at the moment, it's just very difficult to say. The plots here have not really been thoroughly investigated for systematics. So we really need to go back and do that homework before making any firm conclusions.
But is it also correct to say that even if one was to just try and speculate, it's not looking in either direction at the moment?
That would be a speculation, yeah. But as I say, we need to do our homework.
Would it be fair to say that you do actually expect, because of this lensing effect, a bias in the Hubble diagram because of this asymmetry between underdense and overdense, between void and halo, that like it should actually shift it by some small amount?
Well, you've got to be careful with assuming that the Hubble diagram is biased. First of all, gravitational lensing doesn't create or destroy photons. So if you had a big enough sample, you kind of expect this to average out. What we really want to investigate is whether there's any observational bias. This is bias caused by the things that we might need to do to observe supernovae. We're asking the question, is our sample a fair representation of the universe? That's what we're really testing here.
Early on in supernova studies, we were worried about whether gravitational lensing could bias it because of this magnification effect. But it's been known for a long time that the mean is not shifted, even though you get a skewed distribution. So as long as you have a representative sample of supernovae, on the average at all redshifts, the average is consistent. It's not changed by the lensing. So you don't expect, if you have a complete sample, that there will be any bias. But as Paul said, selection effects could potentially mean that you don't have all of the bright ones down there, or you don't have all of the faint ones, and so maybe there's some small shifts. But one of the reasons that we haven't been particularly worried about this until now is that, as we said before, the intrinsic scatter in the supernovae themselves is about 10 times bigger than this effect that we're seeing. So it's really just a tiny little wobble underneath the overall Hubble diagram.
Yeah. That second part I had already absorbed, but I guess the first part, the mean is unaffected, I guess, then, because even though more of the lines of sight, so more supernovae will have been along underdense lines of sight, there is this kind of cap on the size of the signal, whereas on overdense lines of sight, it can get much bigger, so that the average still averages to zero. Is that a fair thing?
Which is why if you're making cuts on your supernovae, you should be really cautious and not cut bright ones just because they're bright, because you need those bright ones to average out the many faint ones.
Another question I was very curious about when you were showing like the sort of scatter of delta M values, I presume that this is definitely something that will be a future thing, but maybe there's just not enough power to do it now. But could you construct a correlation function of delta M's to kind of be looking for the power spectrum of the gravitational potential that is causing the lens delta M to occur. The same way that you have a cosmic shear power spectrum. That in principle you can detect the cosmic shear signal without doing any modeling, because you're just seeing that the skewness is correlated. You could see that the delta M here is correlated.
Yeah, this is definitely something that we thought about. Yeah, and we tested for. So the slight problem with doing this is that the amount of scatter that you expect from large scale fluctuations, i.e., linear scale fluctuations, is just so much smaller than the scatter you expect to be caused by the halos. So when you look at where the supernova are on the sky, they're quite widely separated. So in principle, yes, two neighboring supernovas should be correlated in their brightnesses. But in practice, at least for the DES sample, that effect is just too small to detect. In future, however, it may be possible to detect it.
Yeah, so the actual scales probed by the supernovae are large scales, but the effect is a small scale thing. So you can't measure the power spectrum on small angular scales with the supernova yet.
Yeah, it's there probably, but it's too small to detect at the moment.
So a related question to that is, I guess, you've used the DES galaxies to estimate the line of sight gravitational potential, I guess, eventually, by saying how many galaxies there are. Could you do this maybe even more directly with, say, like a CMB lensing reconstruction of the gravitational potential? Like they have these beautiful maps of what they have essentially measured the convergence to be along various lines of sight. Could you kind of use that with your delta M's and say, like, okay, ACT told me that along this line of sight, my delta M should be this value? Is that feasible, or just you have to start somewhere and you haven't done that yet?
Yeah, it's a little different with a CMB lensing. So the CMB is a much more distant source. So remember I said that lensing is at its strongest when the matter that's doing the lensing is kind of halfway in co-moving distance between us and the source. So that means because the CMB is further away, it's also picking up matter that's further away, mostly, than our supernova sources. So it would be great, but unfortunately, yeah, the CMB lensing is just further away. It's sensitive to distances that are further away than our supernovae are.
But maybe you could use the cosmic shear data then, I suppose, to a.
DES data also comes with cosmic shear measurements over the field. So one of the things that we were really curious about early on when the first cosmic shear maps came out was whether our supernova fields all happened to be just in an overdense part of the universe or an underdense part of the universe, like, because that overall would give us a slight bias on the cosmology. And so we don't see that, but the cosmic shear resolution is quite big, so you don't have much information about detailed lines of sight with the cosmic shear map. You basically have sort of a bit more information about whole fields that we've observed and whether they're slightly overdense or underdense.
So there is no other observation of lensing that you can kind of cross correlate against.
Well, we can cross correlate with that, but the stuff that Paul's been doing, like the where lensing is really strong, is near halos or through the big voids for de-magnification. So um, it's that those are the most significant pieces.
You can't use any other lensing measurement because no lensing was sensitive to the same scales in redshift, I guess is what you're saying.
Yeah, and this is the fun of supernova lensing is that we are starting to probe these really small scales. Of course, it does limit the synergies that we might have with other data sets. On the other hand, we're really starting to push lensing now into a regime it's never been before.
Dust and like extinction of brightness of supernovae should also be correlated with where stuff is. Is that something one should be worried about, or are there super obvious reasons why magnification just doesn't look the same as scattering off dust and therefore getting less bright and things like that?
Yeah, we looked for dust extinction. So in principle, again, you would expect a correlation between our lensing estimator. Now, if dust kind of tracks where dark matter is, in principle, where the magnification is bigger, maybe the extinction is also bigger. But this would show up in the colors of supernovae. So this is something that we measure in the sample. We don't see any correlation between color and our lensing estimator. But we think, having done some back of the envelope calculations, that this effect will be too small to detect in our sample.
I've already asked a lot of questions that have kind of forced you to answer what's coming next, but is there anything else that is coming next that you haven't already spoken about or answered directly to one of my questions? Where are you going with this effect in the data in the near and midterm future?
Oh, for stuff that we haven't talked about today, I'm really excited about the new low-Z samples that are going to be coming soon. So one of the features of our data is that we need something to anchor the Hubble diagram at low redshifts. And because DES looks at a really narrow part of the sky, we don't collect too many low-Z supernovas, so we have to use some from older surveys. Now, there are a couple of surveys that are upcoming, which is DBAS, and there's wiki transient facilities, and those are just going to be fabulous for anchoring the Hubble diagram. So that's really going to inform us on evolving dark energy, and it's also going to help with the other end of the Hubble diagram because it's really going to tell us how supernovae really behave, how variable their explosions are, how correlated those explosions are with local conditions in the galaxies. So that's going to really help us constrain the bias that we have to correct for at the distant end of our Hubble diagram. So, and both of those are very, very relevant to the question of is dark energy evolving or not. So I'm very excited about these new low-Z surveys that are coming out.
When you say anchoring the Hubble diagram, though, you just mean like anchoring it in a kind of pivot sense for evolving dark energy, not like truly anchoring it to redshift zero and having something to say about the Hubble tension.
Yeah. So dark energy comes to dominate our universe relatively recently. So it's that low-Z sample that is really giving us a lot of information about the evolution of dark energy.
Actually, maybe just going back to my question about the CMB. I know that your answer was very persuasive because I remember now that they kind of have a peak of their kernel at like redshift 1.5 or something, and your supernova are all below that redshift. But they are sensitive somewhat to lower redshifts. Is there no correlation information, or is it again a scale thing that their angular resolution of their actual telescope is not?
I think it's because it's blended. The low Z, there is some effect at low Z, but it's kind of blended with a high Z, and I think it's hard to separate.
I think the resolution of both the CMB lensing and weak lensing shear that's done with galaxies is quite large. So it's smoothed compared to the resolution that you can get when you have a point source in the background and a particular line of sight.
Thanks everyone for watching. At the time of publishing this talk, Cosmology from Home is only just starting, so you can still register if you want to discuss this talk or any of the other awesome talks at the conference. Otherwise, if you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both for you and the channel, and share the channel with colleagues. If you have any questions or suggestions, leave a comment, and check out all the other great Dark Energy Survey Supernova talks from this release. Other than that, thanks Paul and Tamara for the great talk.
Thank you, Sean.
Thanks for having us.